Okay, so in regards to trusses have, I guess, for want of a better term, really opened up the possibilities of building. If we particularly look at timber framing over the ages, started with some fairly simple structures. Have either of you guys ever seen what's called a half timbered house? Right. There's not many of them in SA. There's a couple. If you head up the freeway toward Murray Bridge, get to about Harndorf there's this tiny little town which is cut off from Harndorf when the freeway was constructed. And there's just this tiny little hamlet of these half-timbered houses just there, so built by German migrants that came over with Captain Hahn for Harndorf, whatever. They built those now. I'm sure there was a few of those built around in Harndorf itself as well, but Harndorf being a place which is sort of grown and whatever, sort of a bit demolished. I'll do a quick Google search of an image for a half-timbered house, because I'm sure it's one of those things that when you see it, you go, oh yes, I know those. So it's that classic Bavarian looking.
Yeah.
Well, actually, that kind of that one there sort of shows it all without all the infill. So we actually do have a few of these in South Australia. So that's I guess that's sort of the early style of timber building, the first approaches to timber building that truly produce sort of a modern structure. And it's about a series of uprights, a series of cross members, essentially producing portal frames like we went through a few weeks back. If we strip all this out, what we've got here is a portal frame. What they didn't have back then is steel for making joining plates, etc., or steel for nails and whatever. And so to get around that, used diagonal members for bracing and strutting. So when there's a load on this way, this acts as a strut. When there's a load pushing the other way, it acts as a brace, being diagonal like that. And then some intermediate pieces here for fixing all the brick infill or stone or mud and straw, whatever they want to use. And then all these bits are dowel fixed. You've got mortise and tenon joints and dowels going through all that type of construction. So that's where we've evolved, where our building has evolved from in that sense. I guess you guys would have seen a lot of modern timber frames about the place. We've got upright studs, noggins between top and bottom plate, ties it together, and then roofs pitched in, using rafters and under purlins, strutting beams, all that sort of hanging beams, etc. Where we went on from that traditional way of pitching a roof is to produce a truss. Now, the truss, I guess, essentially, it's like a portal frame in that it is, it produces a structure which braces itself and it's rigid, but it's almost the antithesis of a portal frame in that portal frames rely on the brute strength of the simple elements that make them up, whereas trusses use bracing and strutting to produce a solid piece from as little material as possible. So trusses are particularly lightweight, pick them up, pass them onto roofs. So here's a couple of examples of trusses. These, you can probably see that from back there. That's a pretty funky but low-tech approach to a truss. So we've got doubled members, top and bottom chord, and then webs in between that, dowel joints, and so on. So that would be something that's likely to be exposed and to be visual. That's our standard sort of truss that we'll see. The thing about trusses is it means you can get really big clear span within a room, and so it means you don't have any load-bearing walls, so you've got complete creative control of what happens under that roof structure. Some limitations with trusses are that trusses have to be manufactured off-site, and it's not the sort of thing that you will manufacture at home. You don't go, oh, I'm going to whip up a couple of trusses to go on this roof. So there are limitations with design in that regard, or sometimes it's easier to truss the majority of a roof and then just leave one piece for pitching on site, bits that are a bit odd or funky or whatever, that are too difficult to draw up and convey to a truss manufacturer. Although truss manufacturers are getting better at this as well, in terms of you being able to supply them with a roof and all the design information, and then they go ahead and produce trusses there. So a bit of background. Since our first attempt to enclose space for shelter, the most challenging process of building has been carrying the loads over horizontal distances without touching the ground, so spanning between two supports. So, first sort of approach doing that, simple rafters, skilling and roof, and that still has its application. There's still plenty of places that use, like a skilling roof and long and straight rafters, and that has also, I guess, once again been extended in its possibilities also via trusses as well. So the not your standard A-frame trusses, but things like ladder trusses and your floor joist type trusses, which we'll have a look at a little bit later on. So designed to span between external walls, simplifies the roof system and its construction, factory made, available and installed in accordance with AS 4440. So that's an Australian standard you probably will get to know fairly well. I guess one of the golden rules about, or one of the things to simplify it down into one golden rule with AS 4440 is that there's typically throughout that standard there's 50mm tolerance for things. So you're allowed 50 millimeters tolerance for placing the trusses, 50 millimeters tolerance between from vertical, etc. So you notice that 50 millimeters applies through many aspects of installing trusses. Can be designed for most roof shapes, preferred for simple designs, rectangular with gable ends. Careful consideration of wind force in the roof and position of walls to transport loads to floor slab. So that's the same as with any roof. Also attention to anchorage for the trusses to resist uplift. One of the things about a truss roof is because you're spanning from point of support to point of support, which might be 15 metres apart, you've got a huge amount of roof upload width to tie down. So your tie downs are going to be quite significant on the ends of your trusses, and they may not be with a pitched roof with intermediate supports. So what open spaces require trusses to be designed by a professional engineer? Yes. But that's all getting much simpler. So it's about simply providing your roof design to a truss manufacturer and saying, all right, can you manufacture these trusses for me? And by and large, that's getting much cheaper than being able to pitch a roof. So you can get that done very, very cheap. And then, installation on site. So you save on.
Sorry, Michael, I can't bring up that.
Oh, yeah, sorry.
Is that on here? Or?
Yeah, no, it's not. No, sorry. I mentioned before.
I gave up looking for it.
What's that?
I gave up looking for it.
Oh, sorry. I just quickly. Sorry, I quickly mentioned. I'm just grabbing this out of the deployment because. Right, and I said I'll have to shunt it in at some other time. Put it into this subject because
there wasn't many options there. There was only.
Yeah. Sorry about that. No, you're gonna have to. Yeah, you're gonna have to look on the screen. I'm sorry because that hasn't been put into this subject, but we're meant to be covering trusses tonight, and floor trusses, and I thought, how can we really go into floor trusses without actually covering roof trusses, really, to really understand how trusses work and are manufactured, because so many of the elements are the same and the principles are the same. So hopefully I'll be able to drag it into this subject sometime and work that out. So advantages of trusses: lightweight construction, so don't weigh very much, large, clear span underneath. Open web construction for easy installation of services, and that goes for floor trusses as well, as we'll see later. Factory quality control, consistent size and shape, because they're all manufactured within a factory. And yeah, here we've got the jig there. So the jig is set up for, they'll from your truss plan, you'll probably have a bunch of trusses at the ends, which are all different, particularly if it's a hip roof or something. But in between your hip through to your other hip, probably going to be like 19 or 20 standard trusses. They're all exactly the same. So they have a jig set up there, and it's about just dropping all the pieces in and pressing the plates in. So they're all going to be exactly the same. So factory quality control, consistent size and shape, less timber required, speed of putting them up, versatility of design, and cost, because a lot of the wastage is minimised as well. So on site, typically you're cutting off bits of timber this size, whatever, and then they get chucked, or they might get used for noggins, but decent amount of wastage that happens on site. Whereas within the truss manufacturing process, they're using tiny bits of timber all the time, so all these bits and pieces get used up. So not just timber trusses, but steel trusses, and not just small trusses, but massive trusses. I'd hazard a guess at probably that truss is going to be about the biggest truss you're ever going to see, transportable wise, because you've got limitations on the width of a load that can go on semi, and also the length of a load that can go on semi. So standard sort of transport sizes are maximum size of 15 metres, and you probably know more about maximum lengths for transport. Yeah. So 15 metres about your max typically, but you can go to 18 metres.
We basically on shipping containers, so 40 feet. So yeah, everything we go is about 12 metres, I think.
Yeah. 40 divided by 3, what's that?
So it's about 12.8.
Yeah.
12.8.
Yeah. So I've been told that 15 metres is pretty much your maximum standard transportation.
Yep.
On a semi. Maybe that has some overhang on it also. But I'm not sure about what you need insofar as police escort whatever for 18 metres.
Yep.
But typically you don't want to go over 15 metres for any of your construction lengths of stuff. But then also you've got your widths to worry about as well. So I guess that sort of truss is not too difficult to transport. If you've got a bunch of them, they can stand up. But if they're sailover trusses, whereby the top cord extends past the bottom cord, well then you've got other issues in transporting them as well, and they might have to lie down. Anyhow, I guess if you go ordering these trusses, the truss manufacturer, they're going to tell you that anyhow. They're going to say, well look, okay, we can make them, but we can't get them to site. But not just timber trusses, so plenty of light gauge steel trusses. And when we look at the light gauge steel framing houses, so there's a lot of that being designed now, whereby your light gauge steel framing manufacturers, you get them a floor plan, and they design a walling and roofing system for that. Predominantly, so their roofs are almost exclusively trussed with light gauge steel framing, but then the wall sections are increasingly incorporating trusses in the walls to create the wall sections as well, moving away from our standard studs and noggins and actually producing lots of tiny little trusses. Trusses for lintels, openings, etc. So there's, actually I don't know what that that truss with the curved top chord is called. Maybe we've got it in here. Yeah, various different types and approaches to trusses. So some absolutely massive one. I dare say that was manufactured on site. I've got a bunch of forklifts under that. Composite trusses. So here's trusses manufactured from timber top and bottom chords with steel webbing between, and then you've fairly standard timber trusses. Once again, fairly standard timber trusses. Note that these trusses incorporate a vertical strut in the truss where they cantilever. So we've got trusses cantilevering to create an eave. And a sail-over truss to produce a raking eave. So we've got our top chord that extends past the top plate. So this is our top chord here, our bottom chord along the base, and our webs. Also notice in here, each will be intentional compression according to the type of truss involved, and also according to the situation, the loads imposed. So at times, this will be under tension or under compression, depends on what the wind is doing. If we've got wind heading from this direction, pushing the load down on that, well then that becomes in compression, which is forcing this one to bow, which puts this one under tension, which pulls against the top of that. That one ends up being in compression, etc. So you've got these interactions happening within a truss. So bottom chord defines the bottom member of the truss, usually horizontal and carrying combined tension and some bending stress from gravity loads. Top chord defines the top members of the truss, usually sloping and carrying combined compression and some bending stress from gravity loads. Webs and members joining top and bottom chords to form a truss, there may be tension or compression depending on the truss design. So the majority of trusses through a standard rectangular shaped room are pretty simple until you get to the hip end. Once we get to the hip end, then things get a bit busier. So we have a whole different series of trusses. So, and typically the location of a truss. So this is our ridge, or the top of our hip, where the hips join in to our ridge. That's called the first station. So first station, second station, third station. That truss at that third station is typically a girder truss. So girder trusses are trusses that are much stronger, and they're the trusses that pick up all the load from our jack trusses. Will essentially take up the whole load from our hips. Now those girder trusses can be at either second or third station, but typically they're at the third. Exactly how truss manufacturers work that out, I'm not sure, but there must be, I'd say there's a rule of thumb about it's somewhere around the 2/3 distance there. So we've got 1, 2, 3, 4, 5, and we're at the third, so it's about half, really, about halfway. So that's our girder truss. Now, girder trusses, because they're sitting there at that second or third station, they're typically truncated. Truncated means the top is cut off. So, our standard truss, our standard triangular truss is not truncated, but our girder truss, because it's got these other sections of hip going over the top of it, the top of it's cut off. So it's called a truncated truss, and that's a truncated girder truss. So that's the one at our third station there. is our truncated girder truss. The one at our second station there, that's just a truncated standard truss. So that one isn't going to be heavier in construction because it's the only load that it's carrying is that bit of top plate that goes from the truncated girder truss through to our first standard truss. It's only carrying a small amount of load.
So it's lighter timber members?
Yeah, lighter construction, yeah. So our truncated standard truss is going to be the same size timber members as the rest of our standard trusses throughout. It's only the girder truss which will be made of much heavier members. Other trusses involved here, we've got creeper trusses, which are small trusses that head up to our hips. And then we've also got hip trusses in here. Do I have? Oh yes, we do have those shown. So our hip trusses have this section here that meets the girder truss. And as do our creeper trusses as well. Standard trusses performed an outer triangular shape, typically resembling an isosceles triangle. Many web layouts within other triangles are used to address spanning abilities as follows. So king post truss, you might have seen some of those, old warehouses, that type of thing, where basically all we're doing is joining our ridge to our ceiling joist. And queen post has 2 additional webs. So type A truss is the most common truss that you'll see about the place. So no central web, instead the truss span is divided into 3 panel lengths with webs spanning outwards from each, spans up to 9 metres. And type B has additional webs, and they'll span up to 14 metres. Truncated truss takes the standard shape, cuts the top off. Now, have either of you seen floor trusses before? Yeah. And so, yeah. So we're getting pretty close to that sort of scenario, aren't we? If we, chop that off, and you'll see a lot of that shape incorporated in steel frame walling systems now as well. So cantilever truss, so that's like where we saw those eaves constructed earlier. Although one thing I would add is predominantly when I've seen cantilever trusses, you have this web shooting straight up there at that point, working directly as a strut. Cut off truss, not something you see all too much, but with some odd or interesting roof designs, we get such a scenario. And half truss, so cut off at the apex or basically producing a skillion roof. So this is basically just rehashing stuff I'm sure you already know. So roof rafters and ceiling joists will sag over time. So it's about producing webs inside there to alleviate that. So this is your standard form of pitching a roof. So to counteract a lot of that sag, there are a lot of other members introduced and a fair bit of complexity introduced into the roof, and a lot more design work required. So we covered standard pitching of roofs earlier, so yeah, you guys are fairly cool with that. So trust the engineer to help in following ways. Much lighter timber members can be used. Lighter timber can be predominantly sourced from plantations and easily kiln dried, so then no surprises as they dry out. So with our standard Pinus radiata, that can be kiln dried in a couple of days. You know, which is much quicker than a lot of your hardwoods, which I think are like 6 weeks or so. And your other species of timber, you know, that might be required for other forms of roofs, much quicker than that. Although also engineered timber, so laminated veneer lumber, these type of things, it's making the possibilities in standard in conventionally pitched roofs much easier once again as well, because you can get very large pieces of timber, very strong pieces of timber that take very big loads. So a roof frame can be planned and prefabricated off-site, making it more possible to take advantage of, I don't know what they're saying over there, but saving time on site anyhow. You can put a camber or pre-design a camber into a truss to produce a slight camber, so that when we apply loads, particularly tile roofs, that they will settle down to their desired location. There's not such an issue with sheet roofing. Sheet roofing is about 10 kilograms per square metre. Tile roofs are around the 90 kilograms per square metre, so we're talking significantly larger loads on a tile roof. Although, when it comes to ceiling joists, so with our tile roofs, we have our trusses at 600 centres, so 600 millimetres apart. With sheet roofs, we have our trusses at 1200 millimetres apart. That does pose a problem, or not a problem, just another thing you have to do when you do a sheet roof with tiles. A sheet roof with trusses, is that you have to have intermediate ceiling joists, because all your bottom chords are at 1200 centres, but your fixing points for your plasterboard are at 600 centres. So that might require that you have a whole series of steel top hats going on the underside of your trusses that you fix your ceiling lining to, or you do intermediate ceiling joists. And those intermediate ceiling joists can be hung with hanging beams on the inside of on the bottom chord of your trusses, and then join your intermediate ceiling joists in there as well. So a couple of different ways, but that does have to be addressed. So benefit trusses, they can span long distances one go. Internal walls cause problems if used for support because they change the way the truss works. That is an important consideration. So because trusses are designed to be, you know, at times in tension or compression, and to deflect and transfer those forces to other members and share the force between other members, as soon as we put a load-bearing wall directly under a truss and we fix that wall to the truss, then that stops the truss acting and sharing the load with its other members. So the way we do that, and probably would have been good to bring in a bracket actually for this, but I'll draw one. So for our wall, so this is our floor. I've drawn this wall incredibly short. So we've got a bit of top plate on our wall, and then our truss is heading across like that. We leave a very small gap between the top plate piece of timber on our wall, and then we fix that with an L-shaped bracket. So the bracket's going up to here like this, and it's L-shaped. If we were to look at it in this direction, it's like that. And then we have an oval-shaped slotted hole there, and you fix it with a nail, but you don't drive that nail completely till it holds it fast in place. You only drive it till it's sort of, till it's snug, but there's some movement. So that bottom chord can still move up and down while that L-shaped bracket fixes that wall in place. So, yeah, I'm not sure the clearance you need there, but it's a small amount of clearance, 5 millimetres or 5 to 10, something like that. And then, of course, what you don't want to do when you've got cornices is you don't want to attach your cornice to both the wall and the truss, because if you do that, well then you get splitting here at that point. So what we ideally want to do is fix our cornices to the bottom of the ceiling, our plasterboard ceiling, and not fix it to the wall, so it can actually move that tiny little bit. We're talking about very small movements, but once you do go fixing that, and that bottom chord moves a little bit, you get ugly cracking along the bottom of your cornice. Yeah, well there we go, there's some of the L brackets there. And for load bearing walls, use triple L grip. So that's a triple grip, so you can get a whole bunch of nails in that, and that provides a lot of tie down to your truss. And you can use one of those on either side of your truss as well for areas where you've got more uplift. Well, that's interesting. Bottom truss bows upward in winter. So possibly as a result of taking in moisture, some more ambient moisture in the atmosphere, we get expansion of timber. When timber expands, it needs to go somewhere. I assume that's what's causing that scenario. So, there we go. The curved top plate or top chord truss is called a bowstring truss. So when seeking council approval, the owner must provide the following information: type of roof covering, or when getting a roof designed by the truss manufacturer, what that means. So type of roof covering, pitch of roof, winter category, actual spans, and ceiling lining. When ordering trusses, the following information must be provided: house plan, correct spans, special loads, and special conditions. Thinking some of those special conditions might be transport, manoeuvrability, on-site, construction on-site, any issues surrounding that, like site access, that type of thing. Special loads might be solar systems, roof-mounted hot water systems, air conditioners. So factors affecting the design of the truss: span, pitch, wind category, and roof design. So with a very rectangular house, it gets very easy. When we have, a whole series of ranch corners and rooms and things like that, the truss design gets more complex. So we saw the complexity of a hip end there. When we start getting scenarios of floor plans that are like, let's do some more things on that. Like that, for example. Then pitching that gets a little bit more complex. The way we go about that is you go there. We've got a thing there. We've got one coming up here. We'll have that there, etc. So that's the way you end up working out what your roof is going to do. Yeah, whichever way that one, whether that joins into that or not. But you end up getting these scenarios where you go, okay, that's what our roof is going to be doing, and then you go, right, well, in this bit here, for that thing there, we'll have some standard trusses heading along there, but then we get to this bit where we've got standard trusses underneath that already. What we'll have to create that little section of roof are what are called saddle trusses. So, the thing I wanted to illustrate is it's fairly simple when you've got a square plan. When you start getting other things, other sections on there, then there's all these tiny little trusses that start getting involved in that. So, like that, for example. How clear is that? It's not. it's not really clear what we've got happening on there. Yeah. It's not a great example because we can't read any of these, any of the specification of our various types of trusses on that. So, yeah, this one, there's not too many weird things going on. So a lot of standard trusses through here. We have a cut-off, a truncated cut-off girder truss happening in that scenario, which links up to this other girder truss in there, which is picking up a lot of this load, and we've got a hip truss in there to create that. Some creeper trusses coming up to that, some cut-off trusses onto this side. So there's some interesting things happening in that corner there to create that corner. But beyond that, there's just a lot of standard trusses. I'll have some half trusses here because we've got basically a half roof through that section there. And a very interesting girder truss happening in this scenario here. The rest of that's fairly standard combination of hip ends. So, hip trusses, creep trusses, jack trusses, and standard trusses. So actually, I'll quickly flick back to our hip end there as well, just to reiterate, remind about those types of trusses, because that will cover essentially the vast majority of trusses you encounter. The only thing that doesn't cover are what are called, I used the term just before. This is mine. Saddle trusses, sorry. So, saddle trusses, and I'll try to draw it up larger. Clear off this section here. So, I'll draw it in elevation like this. So this is our house there, that, and then we've got another, like what's called a minor ridge coming off that. Let's say it ends in a gable end like that. So that's our roofing situation. Let's say we've just got a gable end here. Keep it all quite simple. So to produce this, we have standard trusses coming down through here like that, and this one's got some standard trusses in here. That, as soon as we get to this point here on this roof, we have a series of trusses that are all standard trusses going back in there. Now, as those trusses become internal, inside the house, an internal wall, the top cords aren't going to sail over to create an eave, so they'll be all cut off. But they will continue through that roof. So if we're looking at that in plan, they're all continuing through there like that, and then we have some large beam picking those up. So that's these trusses here, standard trusses continuing through there. As we get to this section here, so our standard trusses here, much smaller, we need to create a pitched section that comes up to there, and that will sit on top of these trusses that are already here. So we use tiny little saddle trusses going on there that sit on top of our standard trusses just to create that portion of roof, that bit there. So beyond those trusses that you see required there to create a hip end, or between those and your saddle trusses, you're pretty much covering 90% of the trusses you'll ever see used in a roof. Beyond that, like we've seen in this model here, we've got a couple other funky looking trusses happening in there that are sort of case specific. Things like like this fella here, a truncated girder truss that's cut off, so cut off the truncated girder truss, that sort of thing.
You could probably, if you wanted to go, say, 15 metres and then another 15 metres, if you had a beam designed to support the middle,
yes,
have two,
yeah,
half trusses.
Possibly. That'd be a question for the truss manufacturer to see if you can do a half truss that'll span 15 metres. So typically your A type truss, you can extend them out to be that size. Whether you can do that with a triangular like half truss or not, that'd be a question for a truss manufacturer. But yeah, certainly for making transport possible, that might be the way to go. Although that's a roof spanning 30 metres width, so an open floor area of 30 metres is pretty big roof area as well. What we use for doing our steel, the roofs on our steel tanks, they're still only 13 metre long trusses, but we do them in two sections with flat plates and bolt them together on the middle, so they get transported as two halves bolted together on site before being lifted up. So it's another way of doing that as well, to produce two halves like you say.
And how big are they when they're together?
When they're together, that's spanning 13 metres, so it's still not huge. But they wouldn't want to go. Well, actually, I don't do a lot of lifting. My brother does a lot of the lifting for getting them up because they're heavy as. It takes three of us, one person supporting the middle. So beyond steel trusses, beyond that, starting to get a bit too heavy for them, and as well, which is also an issue. So if you have to crane stuff in, if you're paying $500 an hour for a crane, that's a cost that has to be factored in as well. And certainly if you're building out whoop and it takes a couple of hours for that crane to drive there, you're still paying for that crane.
Depot to depot.
What's that?
Most of the crane goes depot to depot.
Yeah. So, you're paying for that time as well as the time on site. Yeah. So making your trusses, in smaller sections like that, and then putting them together or finding another scenario is also a significant cost saving. So what we have happening here in this truss diagram, so probably would have been a good one to show you just before. So we've got a couple of hip ends here, H3, so that's a hip truss. C, these are our different numbers for our creeper trusses. So the creeper trusses are the ones that go to the hip truss. So our hip trusses here, they're the ones that go into that. This is our truncated girder truss here. So TG4, truncated girder truss number 4. And I could, without even reading that, you can tell that's a girder truss because all of a sudden the names switch from being C, so for creeper truss, to J for jack truss. So jack truss, we know that joins up with a girder truss. So that one there must be a girder truss. And so these are your standard trusses, TT. Typically I've notated them as ST, but I guess ST does get confusing when you've got a series of saddle trusses in there. So ST might be for standard truss or used for saddle truss. So here we've got our ridge joining up. So ridge joining up with our hip, which comes slightly lower than that major ridge there. So we have a whole series of saddle trusses in that bit there. So that one, that's actually been grabbed from diploma, as I mentioned earlier on. I'll just get out of that. open up. So, couple major truss manufacturers. You know, you've got Prida, who produce trusses, and they produce a whole series of metal fixings and metal products for building, so lintels and things like that. So, and you've also got Mytech. So you've got your various different truss manufacturers in Adelaide, but they're either using Prida products or Mytech products. Right. So have a look at the Prida stuff first. So Prida floor and rafter trusses. So our floor trusses, that's the trusses we use to create flooring, and rafter trusses, that's what we were talking about just before. So that's all our roofing. So timber for these trusses is on flat. So talking about floor trusses, provides a stable platform during installation and minimises the overall depth required. All trusses are commonly available timber, and most floor trusses in Australia are made from 70mm or 90mm dry timber. So two different types of web systems. One, long reach truss is all timber webs, and then while Prida span uses metal webs for the diagonals and timber webs for the verticals. Have both of you seen those composite trusses where you've got the metal W's? Yeah.
Yeah, I've spent a bit of time looking at this.
What's that?
I've spent a bit of time looking at that Prida website.
Oh, right. Yeah.
Reading through it,
Yeah. Okay. Yeah. So, Prida long reach trusses reference FT 200, 250, 300, 350, etc., 400. FT means floor truss, and 200 is the nominal overall depth. The actual depth dimensions are nominal sizes or may be individually specified as required for a particular project. And yeah, with Prida span trusses, PS25, PS30, etc., for 250, 300mm, etc. So manufactured using light gauge metal webs and lighter than long reach, but this is considered during the design process. So yeah, just your standard sort of cost benefit, sort of selling the product type of thing. Design benefits, so long span capacity up to 8 metres or more, offers functional design freedom and eliminate the need for interior support. So 8 metre spans, that's pretty decent for a floor. The depth suit wide range of standard depth available from 200 to 450mm. That's all fairly standard. Right. I'll now have a crack at the Mytech website. Has a couple explanatory videos on there for their trusses. Australia. So once again, they're doing very much the same type of thing. Actually, no, we should go to the. I'll go to the Prida site again in a minute, because also what they're doing are these posi strut cassettes. So have either of you seen these before? Yeah. Okay. So you use them, or?
They've come to a job or two and they've gone in, so.
Yeah.
But I didn't put them in, I just,
Yeah.
I've seen them go up and, they don't look like they're strong, but they are.
Yeah. Yeah.
And then that other type where it's like It's like brace board down the centre of them,
Okay.
and then 90 by 35 top and bottom.
Oh, right, yeah.
And
So,
they
yes.
look even less,
Yes, yeah, less
where the
rigid.
strength is.
Yeah. That's your, like, if we were to cut through it, we've got top chord of a piece of timber, bottom chord of a piece of timber, then it's essentially a piece of plywood in between. Those ones, yeah. Engineered timber, timber I-beams. Yeah. They don't look so strong. Although, actually, I've got a piece in the storeroom which is actually really solid stuff.
Just like with those, I think plumbers have a bit of a problem.
Right.
Because when they try, if it's 2-story and they're trying to run sewer pipes, and
Yeah.
they run out of spots to go.
Yeah, and you can't modify them at all. What you don't want to do is do any modification to them because they're designed to work as a complete unit, and you can't just go snipping webs or something like that. Yeah, to get pipes through. Now, if plumbers are having an issue, that's really an issue with the designers not thinking about the plumbing runs and the fall, the slope relationship you need within your pipes over a distance. It's about designers just putting in toilets without thinking that they're going to have to run that 100 mil pipe over a distance and have a particular amount of fall over that distance before it needs to get out. Because
they try and design something below it with a lower ceiling, or
a
room below it that's got a drop ceiling in it.
Yeah, and that might be a scenario whereby a 300 deep truss or a 250 deep floor truss is going to do the job span wise, but isn't going to do the job clearance wise for enabling the amount of fall you need over the distance for your sewer pipe, for your toilet waste, but also for air conditioning ducts as well. So for your 250 or 300 trusses, that might not be large enough to get the air conditioning ducts through there that you need. But in comparison to standard flooring systems whereby you have solid timber joists, they certainly make life much easier than the options. I'll just click on that.
To another MyTech building product innovation. MyTech Posi Strut Flooring Cassettes. Many builders and developers, especially those working on large multi-story projects, are specifying Posi Strut Flooring Cassettes. MyTech Posi Strut Flooring Cassettes replicate on-site construction in a factory. The floor is prefabricated off-site to all the relevant specifications. Plus it includes allowances or deflections, reactions, plumbing locations, void stacks, wastes and duct chasers, and recessed wet areas all at the design stage. This ensures there are no interferences when installing on site. The cassettes can be topped with just about any flooring surface. Most opt for particle board, but products accommodating wet or dry areas can also be used. Posi Strut Flooring Cassettes can utilise top chord support for ease of installation. This means they can be craned into position on site and fixed in minutes. The implications this has on site are substantial, with more square metres of flooring laid by less labour in a lot less time. Storage on site is minimised too, as the Posi Strut Flooring Cassettes are installed on the same day as delivery. Plus, once installed and fitted, the cassettes can be walked on, a great advantage when working at heights. It also means the next part of the construction process can get underway straight away. MyTech Posi Strut Flooring Cassettes save time on site and speed up overall construction time dramatically, especially on large multi-residential and multi-story constructions. MyTech Posi Strut Flooring Cassettes, the perfect solution for your next domestic, commercial or light industrial project.
So of course you're going to save on time for installing them on site and save on labour there, but I guess you pay for the labour and the manufacturing within the factory as well. So it's about getting quotes and comparing the two. But but certainly that thing of speeding up construction on site enables you to, externalise a lot of that work.
Welcome
and actually have
to
your
another
construction
MyTech
process
building product
much
innovation. MyTech Posi Strut Floor Trusses. MyTech Posi Strut Floor Trusses are open-webbed parallel cord trusses that are ideal for a variety of flooring applications. When used with MyTech's unique load-sharing strong back bracing system, Posi Strut floor joists deliver a rigid floor structure that's straight and uniform. Posi Strut floor trusses can also be designed for top cord support, which makes them quick and easy to install, and ideal for internal applications where space is at a premium. Costs are also reduced, as there's no need for expensive hangers or brackets. Plus, these wide parallel cords enable the truss to be placed upright where required without the need for temporary bracing. As MyTech Posi Strut trusses are an engineered product, they can be manufactured to length so they're ready for immediate installation on site, eliminating the need for trimming. For even quicker on-site construction, there are MyTech's Posi Strut floor cassettes, a prefabricated floor which has been manufactured off-site to all the relevant specifications. Allowances for deflections, reactions, plumbing locations, void stacks, wastes and ducting.
So there was the. Shall we just go back? This one?
Yep. Welcome to another MyTech building product innovation. MyTech Posi Strut Roof Trusses. MyTech Posi Strut Roof Trusses are engineered open-web parallel cord trusses that are ideal for a variety of roofing applications. They can be designed to suit almost any roof application, with clear spans up to 8 metres. This allows architects and designers a greater degree of flexibility and the opportunity to introduce some exciting dynamics into their designs. Low-pitched flat roofs have increased in popularity as owners seek the appeal of high ceilings but are often hampered by building height restrictions. Height limitations can also be an issue with two-storey homes where sloping sites make traditionally truss roofs not viable. Even cathedral ceilings can be easily accommodated with MyTech Posi Struts. MyTech's Posi Strut trusses are easier to fix, easier to manoeuvre, and easier for following trades. Their open-web design makes them much lighter than solid timber beams. Lighter weight design invariably leads to safer handling and faster installation times. Posi Struts provide ready access for plumbing, electrical, even air conditioning duct. Welcome to another MyTech building product innovation. MyTech's Posi Strut, one of MyTech's most innovative.
Alright, we'll leave it at that then. Back into this one. I'm not sure where the link is within here because I found it through a Google search. But basically, prior to doing those flooring cassettes as well, I just wanted to show you that they're doing so basically they're doing exactly the same. So here we go. No, we don't. What's the link? Oh yes, it is just really slow to open. cassettes arrived to having half the floor done. It's pretty good, isn't it? Yeah, so yeah, what was that 3.5 hours or so for doing a floor? It's pretty quick.
I wonder if they check, I guess it's all ordered before they even put the walls up, otherwise
Yes, yeah.
they're waiting too long.
Yeah, exactly. So it'll be staged. So they'll do the plans and then go, okay, we need to order roof trusses, flooring system, order the windows straight away because you get onto the ordering windows before about 4 weeks before you start doing your frame. Get all that ordering happening, then pour your concrete slab and do your site works and everything while all that stuff is being manufactured. So you give them prior to a date for, okay, we want the truss on the floor cassettes on the site at this date. You probably just think through the process. So you want about 8 days of curing on your slab before your wall frames go up. You can get those very simple wall frames done in a day, but probably allow several days for that. So we're at almost 2 weeks, and then your floor trusses can go in. So 2 weeks from pour, roughly. Yeah, I'm not sure what sort of turnaround time they have for production of those things.
Pretty common now to go 2-story, isn't it?
Yeah.
Everyone's got the smaller blocks and then they go 2-story. No, in our street you wouldn't have a crane because the power lines are there.
Oh yes, yeah. And so that's going to be So that's going to be a limitation, isn't it? You go, say, okay, can't get a crane on site, or some sites can't because of the access, can't get a crane on site, and then so then you're not going to use one of those systems because I don't know what they weigh each, but I dare say they'd be a bit too heavy to lift into position with people power. So Yeah, we've actually gone through that super quickly. Sorry,
Let's go to the toilet.
yeah. So I haven't. Well, we had a guy come in from Chevron Glazing.
Yeah, I was going to try and get here. I just been smashed.
Yeah. No. It's good. Well, it's a good thing you didn't actually. Cause what happened? He ended up coming in at 10 o'clock instead of 11 o'clock. So
Right.
yeah. So you ended up being early. But Joe videoed the whole thing, and I was hoping to have that video up, but it's not available.
Yeah, no
So we can't. Not going to get into doors and windows today for that. And and I haven't prepared lining, so I thought we'd spend a bit longer on roof floor trusses, but we'll sail for that really quickly. How's assignments?
My assignment's going pretty good. So really, all I've got left to do is